In this video, we will explore Newton's three laws of motion. These are a series of idealized rules which can be applied when working with ideal single-point masses. Understanding these laws is essential towards solving almost all motion problems. Newton's first law states that an object at rest tends to stay at rest, while an object in motion tends to stay in motion unless acted upon by an outside force. We demonstrated this principle in the following two clips. Here, we see a plastic bottle sitting at rest on a table. The summation of all the forces acting upon this object are zero, as it has no net acceleration. If the sum of all forces equals zero, then the derivative of velocity in respect to time must also be equal to zero. This free body diagram better demonstrates the forces acting upon the bottle. There is the force due to gravity, better known as the bottle's weight, and the normal force applied by the table. This force is equal in size and opposite in direction, giving us a net force of zero. We will now go to our second clip to examine what happens to objects which are already in motion. Here, we see a cell phone resting on the center console of a car, which is traveling at a constant velocity. The center console has a relatively smooth, low-friction surface. Newton's first law states that both the car and its contents will remain at that constant velocity until acted upon by an outside force.
Alright, brake.
When the brakes are applied, the car accelerates in a negative direction due to friction. The phone, however, is not affected by this braking force. The phone is only subject to the negligible amounts of friction between it and the surface it's resting upon. Because of this, it continues in its original direction at only slightly less than the velocity it was traveling at originally. Newton's second law states that the net force on an object is equal to the mass times the acceleration. This law is given as the equation F equals ma. This equation tells us that both mass and acceleration have a direct relationship to force. We demonstrated this principle with a scale, which reads weight. Weight is a force caused by gravitational acceleration and is measured in newtons or pounds. This net force is equal to the derivative of the object's momentum times its inertial reference frame. Thus, force is equal to its mass times the derivative of velocity, which is acceleration. To begin, we first observe the weight of 181.6 pounds. This weight is a product of the acceleration due to gravity and the object's mass. We then decided to demonstrate what would happen if we changed the acceleration while keeping mass constant. To do this, we placed the scale in an elevator and observed how the weight changed during the elevator's initial acceleration. As you can see, the weight on the scale initially increases to 192 pounds while we are accelerating in the elevator. Soon after, it returns to the original value because the elevator has stabilized at a constant velocity. The third law of Newtonian physics states that objects are acted upon by forces that are in pairs. For instance, if gravity is exerting itself onto a stationary object, then the ground will exert an equal and opposite force to gravity so that the object can remain stationary. These can easily be summed up by the equation F sub A equals negative F sub B. The action force F sub A is counteracted by the reaction force F sub B. In this clip, we see a ball being thrown at a crossbar and bouncing back. The ball is exerting a force F sub A onto the crossbar, but since the ball is bouncing back, the crossbar is exerting an equal force but in the opposite direction, F sub B. However, in this real-world example, the force of the ball bouncing off the crossbar is not equal to its initial force. This is because some of the kinetic energy is lost when it hits the crossbar. This energy is dissipated into friction, the crossbar vibrating, and sound. Let us now summarize what we've learned about Newton's three laws in this video. The first law: an object at rest tends to stay at rest, while an object in motion tends to stay in motion, unless acted upon by an outside force. Second law: the net force on an object is the mass of the object multiplied by the net acceleration on an object. And finally, the third law: all forces come in pairs, and every force has an equal and opposite reaction.